Hi, I'm Divashra Nair, and I'm the leader of this group. And these are my group members, Shiv Shakti Nair, Nursuti Nusabrina, and Tashini.
Hi everyone, today I'll be presenting the summary of paper 1, which is titled Cache Out Leaking Cache Memory Using Hardware Trojan, published in 2020. This paper discusses a serious security vulnerability where a hardware Trojan is used to exploit cache memory and leak sensitive information. What makes this attack dangerous is that it can affect cache coherence, even altering unmodified data without needing direct access to the victim's memory controller. The authors emphasize how important it is to secure each system component and prevent unauthorized hardware modifications. This study highlights a critical area in chiplet-based system, and stresses the need for protective design strategies against such advanced hardware-level attacks.
Today I'm going to present about cache memory and analysis on performance issues. This study presents a detailed analysis of cache memory performance and introduces three key optimization techniques, which is which is victim caching, subblocking, and memory banking. These methods help reduce miss rates and access times, improving overall cache efficiency. The paper is well structured using clear explanation diagrams and repeated measurements to support its findings. It also compares these methods with traditional cache mapping techniques, adding depth to the analysis. However, it mainly focuses on random access patterns and does not consider sequential access, which is common in real world use. It also overlooks practical issues like power consumption and implementation costs. Addressing these factors would make the study more applicable to modern system design.
Hi everyone, the paper I review is titled A Computer Architecture Based on Disruptive Information Technologies for Drug Management in Hospitals, published in 2023 by Chalmeta, Navarro Ruiz, and Soriano Irigaray. This paper focuses on medical errors in hospital, which are a serious issue. This error affects about 1.8% of hospitalized patients and lead to 4.6% of hospital admissions. The authors point out 5 key problems in current system. The first one is too many manual processes like stock tracking. Second, lack of full traceability. It's hard to track a drug from arrival to use. Third is poor use of data, like not predicting drug demand. Fourth is regulatory issues, such as not meeting EU tracking laws. And the final one is incomplete records, which is missing info like dose or patient. To solve this, the authors propose a new computer architecture that combines blockchain for secure, tamper-proof traceability, RFID or QR codes for automated drug ID, IoT sensors to monitor storage conditions, and AI with big data to analyze trends and forecast needs. This setup covers everything from data collection to real-time monitoring and decision-making. They validated it through expert interviews, showing its practicality and potential. The strengths include better patient safety, smart use of modern tech, and alignment with EU regulation. But the paper lacking cost analysis has privacy concerns with blockchain under GDPR and hasn't been tested in real hospital yet. I chose this paper because it shows how technology like blockchain and IoT can solve real healthcare problems. Plus, the focus on secure system matches my own interest. Thank you.
Hi, my name is Citron Sabrina, and I'm going to share a review on research paper titled PEDROM, Enabling High Performance and Energy Efficient Processing of Deep Neural Network, published in 2024 by Putra, Hanif, and Shafiq. This paper tackled a major issue in AI hardware, the high energy and delay caused by accessing DRAM memory during a neural network processing, especially for C and N. While modern accelerators are fast, DRAM still slow things down. To solve this, the author proposed PEDRAM, a smart framework that optimizes how data is stored in DRAM to reduce energy and speed up access. What's interesting is that they tested different DRAM architecture, like SWAP and PLD DRAM, and used Pareto analysis to find the best memory layout. The result up to 98% improvement in energy delay product. That's huge. What I liked the most was how flexible their method is. It works across different CNN and memory types. However, I do think it would have been even better if they tested it on real hardware, like an FPGA. Still, the paper gives me a deeper appreciation for how many layout can really affect system performance.
Next, I'll be discussing part B of simulation project, which focuses on how cache size affects performance in a uniprocessor system. For this, I used 10 different cache block sizes and ran tests for 9 different trace files. Based on provided data, as the cache size increases, the cache miss rate generally decreases for most of the trace files. This is because a larger cache can hold more data, reducing the need to fetch data from slower memory locations. However, the rate of decrease varies between different trace files, and in some instances, the miss rate can remain relatively stable or even slightly increase at larger cache sizes. Nextly, my friend will explain it in more detail.
To continue, what my friends present before, yes, indeed, when the cache block are increased, the miss rate will decrease. In this simulation, as the cache size increases, capacity needs are significantly reduced because more data can fit into the cache, lowering the frequency of memory refresh. However, complex misses do not occur in this experiment because the cache uses a fully association mapping, which allows any memory block to be stored in any cache block, eliminating mapping conflict. At the larger cache size, the miss rate begins to stabilize because the cache becomes larger enough to hold the entire working set of data used by a program. In some trees such CEXP, miss rate sharply drops from 40.07% to 1.54% in the cache size 16. This occurs when the cache size crosses a critical threshold, indicating the cache can now hold the entire working set, drastically improve efficiency. However, this threshold differs between trees 5 between each has its own memory access pattern and working set size. Therefore, by increasing cache size, improves system performance, especially in the early stage. The performance can become minimal beyond a critical point, and finding the optimal cache size is the key to balancing performance.
Okay, let's move on to GitHub. To organize our computer architecture group project effectively, we use GitHub as our version control system. As shown in Figure 1, we begin by signing up for GitHub accounts, which give each team members access to collaboration tools. Next, in Figure 2, we created a new repository. This acts as the main folder to store and manage our files and code. In Figure 3, we named the repository to match our project, making it easy to identify and track. Once a repository was created, we moved on to collaboration. In Figure 4, we show the step where we added all the group members as collaborators. And in Figure 5, you can see the invitation link that was shared with them. After accepting the invites as confirmed in Figure 6, everyone gained access to the project space. Then in Figure 7, we published the repository online, making it accessible to all members from any device. Figure 8 highlights the email invitation sent to each member, while Figure 9 shows the invitation alert within GitHub. After acceptance, Figure 10 confirms that the members were fully added. We then begin contributing. In Figure 7, shows how we added text and made changes to files. These changes were pushed to the main repository, which is shown in Figure 12, ensuring our work stayed up to date. Finally, in Figure 13 shows the collaboration history, where each member's contributions are recorded for full transparency and accountability. Overall, GitHub helps us stay organized, collaborate smoothly, and track every update throughout our project. Move on to discussion part for GitHub. Git is a distributed version control system, or VCS, developed by Linus Torvalds in 2005. It was originally created to help developers collaborate on Linux kernel. At the time, existing tools couldn't meet the project needs. Torvalds needed something fast, scalable, and secure that could track all changes in the source code. Git solved this by allowing every developer to have a full local copy of the project, including its entire commit history. This means developers can work offline, commit their changes, and only sync with the main project when needed. With Git, collaboration doesn't rely on being connected to a central server, making it both flexible and efficient. And that's all from me. Thank you.
Now I'll be presenting about the GitHub's discussion. One of Git's most powerful features is its ability to create and manage branches. Each branch acts as a separate workspace, allowing the developers to experiment, fix bugs, or add features without affecting the main project. Once changes are validated, they can be merged back into main hub. Git also keeps a complete record of every change, including who made it, when it was made, and why. This helps track progress, spot issues, and restore previous version when needed. Git's distributed workflow model means that collaboration isn't limited to a single central server. It supports productivity even in decentralized environments, making it ideal for team-based development. Now, when working with low-level programming like assembly language, it becomes even more essential. Small mistakes in assembly can cause entire system to fail. It allows developers to commit small, stable chunks of code so that they can always return to a working version if something breaks. For a project involving multiple languages like assembly, C++, or Python, Git keeps everything organized in one repository. This makes debugging, optimizing, and documenting interaction between high and low level code much easier. Features like Git tips also help track changes line by line, perfect for performance tuning and audits. In short, Git isn't just about saving code, it's about structured, scalable, traceable development. Whether used GitHub or locally, Git gives developers the tools to collaborate smoothly, reduce risk, and maintain clean, organized projects. That's all from me. Thank you.